Hello everyone, my name is Mustafa Zuhair Mahmoud. I am a professor and consultant of radiology and ultrasonography. You are on my YouTube channel, and in this lecture we will go over the geometrical construction of ultrasound transducers. I would like to remind you that today's topic is part of a series on ultrasound physics and instrumentation. To explain the geometrical construction of ultrasound transducers fluently, we must first understand the concepts of transducer construction and its various types, keeping in mind that the basic components of each ultrasound transducer's construction are the piezoelectric crystal, damping block, insulation ring, tuning coil, electric shield, electrical connectors, housing, and matching layer. Let us begin this lecture with a brief discussion of transducer construction. As you can see, the diagrams below depict the typical components of a transducer. As shown in the current slide, the basic components of each ultrasonic transducer were denoted by the letters A to H. The piezoelectric crystal is located at the probe's end, which comes into contact with the patient. The shape of the crystal is determined by the type of transducer and can be spherical, rectangular, or square. The crystal has two parallel surfaces that expand and contract in response to the piezoelectric effect. The two surfaces are coated with a thin gold or silver electrode that serves as an electric link to and from the crystal. The inner electrode is the live side of the electric circuit, while the outside electrode is electrically grounded to reduce the possibility of electrical shock to the patient or operator. In both its sending and receiving modes of operation, an ultrasound transducer is designed to be as sensitive to a specific frequency as possible. The transducer's resonance frequency is the optimal frequency. The resonance frequency of the transducer is determined by the thickness of the piezoelectric crystal. This physical law, which depicts the relationship between three variables, namely frequency, sound speed, and crystal thickness, can be used to calculate any and none of them. Here is an example in which you are asked to calculate the frequency given the speed of sound in the medium and the thickness of the crystal. The damping block is adhered to the back of the crystal, behind the positive electrode, to absorb and attenuate stray ultrasound signals from the housing. One important criterion for the damping material is that it has the same acoustic impedance as the crystal, in order to prevent echo formation at the crystal block boundary, which would return energy into the crystal. The insulation ring's primary function is to absorb energy generated by the crystal's sides. Insulation ring is also referred to as a sidewall acoustic insulator. It's typically constructed of the same material as the damping block. The tuning coil, an inductive component, compensates for the crystal's capacitive effect. As a result, when the tuning coil compensates for the capacitive effect of the crystal, the transducer's transmitting and receiving functions improve. The electric shield is a barrier that serves to pick up unwanted stray signals known as noise. It's worth noting that any unwanted signals picked up by the electrical shield are routed to ground. The electrical connectors connect the transducer to the ultrasound instrument. It should be noted that the electrical connectors connect the transducer to the ultrasound instrument for two reasons, which are to power the transducer and receive the transducer's echo signals. The housing or casing of a transducer is typically made of a highly durable plastic material that is sealed to keep moisture out. I also mentioned that if the housing or casing is cracked, moisture may affect the transducer's performance. The matching layer is a thin layer of material that is applied to the face of the transducer crystal. The matching layer is made of a material with a characteristic impedance value that is between the crystal and skin impedance values. For example, if the crystal and skin impedances were 120 and 30 respectively, the matching layers impedance would be between 120 and 30, for example 75. To summarize, the matching layer's purpose is to reduce the large impedance mismatch that exists between the transducer and the skin. Transducers are classified into two major types based on the number of crystals. Furthermore, transducers are classified based on the shapes of the crystal arrays. According to the number of crystals, the two major types of ultrasound transducers are single-element array transducer and multi-elements arrays transducer. The single-element array transducer's characteristics include the use of single crystal elements and the lack of a choice of multiple frequencies. The multi-elements arrays transducer's characteristics include the use of multiple crystal elements in the formation of the echo pulse, wavefronts from each element combining to form a single wavefront, Huygens principle, and each individual element being electrically and acoustically isolated, allowing flexibility in beam formation. A transducer's shape and field of view are determined by one of three formats: linear, sector, or curved array. As shown in the accompanying image, linear array transducers generate images that are rectangular in shape. Sector array transducers generate images in the shape of a slice of a pie. Curved array transducers combine the benefits of sector and linear transducers and are best used when the sonographic window is large. Please like and subscribe to my channel and click the bell icon to receive notifications of new video updates. I would like to point out that by the end of this lecture, we will have completed the first season of this series of lectures on ultrasound physics and instrumentation, which I hope you enjoyed. Waiting to see you soon in the new lectures of season 2. Okay, see you later. Thank you.